Welcome to Lesson 20. In today's lesson, we're going to be exploring some of the implications of ARM's so-called modified Harvard architecture. So what do we mean by ARM's modified Harvard architecture? Well, taking a step back for a moment, in general computer science and computer architecture, there are, broadly speaking, two main flavors of memory system. We have Harvard architecture memory systems, where instruction memory and data memory are distinct from one another and are accessed over different buses. And we have von Neumann architecture memory systems, where instruction memory and data memory are unified and are accessed over the same bus. Now, on the Harvard side, we call the interface to instruction memory the I side, and we call the interface to data memory the D side. So the I side interface is responsible for fetching instructions and for performing instruction cache maintenance operations. In contrast, the D side interface is responsible for performing loads and stores to data memory and for performing data cache maintenance operations. Over on the von Neumann side, we have a single unified interface which does all of those things by itself. So it fetches instructions from memory, it performs regular loads and stores, and it performs unified cache maintenance operations. Now, the reason the ARM architecture's memory model is described as being a modified Harvard architecture is because it doesn't really fit cleanly into either of those two models. So you'll notice here that close to the CPU, it looks like a traditional Harvard architecture system with distinct I side and D side interfaces to instruction memory and data memory, and separate caches for instructions and data as well. However, as we get further away from the CPU, it begins to look more like a traditional von Neumann architecture memory system instead. So we have unified caches that can hold both instructions and data, and we have a unified bus and a unified main memory too. And in fact, the ARM architecture takes this one step further. So not only do we have separate I side and D side interfaces, we actually have a third interface that we call the TLB side, and TLB being short for Translation Look-Aside Buffer. So this interface is responsible for walking the page tables in memory to translate virtual addresses to physical addresses, performing hardware updates of those page tables, so for example, automatically setting the dirty bit on a page table entry when the corresponding virtual memory region has been written to, and finally, this interface is responsible for handling TLB maintenance operations. Now, the key thing to take away here is the fact that these three bus interfaces, the I side, the TLB side, and the D side, act completely independently of one another, meaning they are each able to issue their own loads and stores to the memory system at the same time. In other words, a single ARM CPU is not just one observer. It is, in fact, three separate observers. So why does that matter? Well, there are three main implications here. The first is that instruction caches are not required to participate in hardware cache coherency. So you'll recall from Lesson 12 that writing to a normal cacheable location involves first getting the corresponding cache line into a unique state before we're allowed to write to it. Unique state meaning we invalidate everyone else's copy of the cache line. Well, strictly speaking, it's only copies of the cache line held in data and unified caches that are guaranteed to be invalidated. So copies of the cache line resident in dedicated instruction caches are not guaranteed to be automatically invalidated when someone attempts to write to that location. Secondly, only explicit D-side accesses are hazard checked for local read and write successors. So you'll recall back in Lesson 3, we saw that accesses issued by the same CPU that overlap the same address are guaranteed to be observed in program order. Specifically, a load overlapping an earlier store is referred to as a local read successor, and a store overlapping an earlier load or store is referred to as a local write successor. However, it's only explicit D-side accesses that are actually hazard checked for these local read and write successors. So if we have two accesses being made to the same location and at least one of those accesses is coming from the I side or the TLB side, then the CPU is not required to keep those two accesses in order, despite them being to the same address. Finally, similarly to above, a DMB instruction also only enforces ordering between explicit D-side accesses. And that means if we do have two accesses being made by the same CPU to the same location, and at least one of those two accesses is coming from the I side or the TLB side, and it's important that we maintain order between those two accesses, then we're going to need to expand our toolkit with a new barrier instruction that provides stronger guarantees than a DMB. Let's step through an example that touches on all three of these implications. So I want you to consider a scenario in which we're modifying the contents of instruction memory. So it could be that we have some sort of JIT interpreter running, which is generating new instruction opcodes and executing them, or it could simply be that we're loading an application from disk into memory, or maybe we're dynamically loading a shared library into a user space tasks virtual address space. So we can model each of these three scenarios using this code snippet that you see on screen. So this store writes some new instruction opcode into memory, and the BR, branch to register, then branches to the location of that new opcode in order to execute it. And well, straight away here, we're going to run into the first of our three implications, that being that instruction caches are not guaranteed to participate in hardware coherency. That means it's implementation defined whether this store will invalidate any stale copies of the old opcode from our dedicated instruction caches. And that means we may need to perform some manual cache maintenance in software. So you're already familiar by now with the DCCVAC instruction, a data cache clean by virtual address to point of coherency, which means flush this data out far enough into the memory system that even a non-coherent observer can see it. Well, here we have another data cache clean instruction, but you'll note that this time it's a DCCVAU, a data cache clean by virtual address to point of unification. Similarly, we have an ICIVAU. That's an instruction cache invalidate by virtual address to point of unification. Now, the point of unification is the point in the memory system at which all three of the CPU's constituent observers are guaranteed to see the same copy of memory. Since ARMv8 and also actually ARMv7 with the multiprocessor extensions, if we miss in the TLB and we need to perform a cacheable translation table walk, then the resulting TLB side access is required to look up in the L1 data cache. So the D side and the TLB side are effectively always unified there. However, in this particular example you see on screen, it's not until the L2 unified cache that all three of the D side, TLB side, and I side are unified in seeing the same copy of memory. With that in mind, let's now step through our code sequence. And we'll begin by assuming that we already have a stale copy of the old instruction opcode present in our L1 instruction cache, which we'll represent using this yellow square. So as we first walked through back in lesson 12, we know that when the CPU wants to perform this write of the new instruction opcode, it's going to generate a read unique transaction to the memory system in order to get a copy of the corresponding cache line in a unique state, meaning everyone else is going to invalidate their own copies so that our copy is the only one remaining in the entire system. And it's the cache line being in a unique state that grants us permission to write to it. So we now have a dirty cache line allocated in our L1 data cache, which contains the new instruction opcode that we've just written. And to reiterate, one of the implications of ARM's modified Harvard architecture is the fact that the instruction cache is not guaranteed to participate in data cache coherency. So it's only copies of the cache line that were held in data and unified caches that are guaranteed to have been invalidated by the CPU's read unique. And that means the yellow square, representing the stale instruction opcode, remains present in our L1 instruction cache. Now, when we perform this DCCVAL, the data cache clean by virtual address to point of unification, what we're saying is, clean this cache line out far enough into the memory system that all three of this CPU's constituent observers are guaranteed to see the same copy of data. And in this particular example on screen, that means cleaning the cache line out to the L2 unified cache. Similarly, when we perform this IC-IVAL, the instruction cache invalidates by virtual address to point of unification, what we're saying is invalidate all copies of this cache line up to, but not including, the point in the memory system at which all three of this CPU's constituent observers are guaranteed to see the same copy of memory. And in this example, that means invalidate all copies of the cache line up to, but not including, the L2 unified cache, meaning the L1 instruction cache. The idea here being that when we come to branch to this location, what we'll do is miss in the L1 instruction cache and we'll be forced to pull in the correct, most up-to-date instruction opcode from the L2 unified cache. At least that's how it's meant to work. But of course, I wouldn't be showing you this code sequence if we didn't need some sort of barriers here in order to actually guarantee the correct behavior. The question is, where might we need a barrier and what barrier might we need? So to begin with, do we need a barrier in between our write of the new opcode and our DCC val, which cleans that opcode out far enough into the memory system that the I side can see the same copy of data? Well, remember, the first question we should ask ourselves is, would it be bad if these two accesses were to be reordered with respect to one another? In this case, yes, it would be bad because we want the data cache clean to clean out the value written by the first store. So it's important that these two accesses are observed in program order. Okay, can they be reordered with respect to one another? And actually, you'll recall from the workshop in part 1 that no, these two accesses cannot be reordered with respect to one another because they're both D-side accesses to the same location. It's worth noting here that while you can think of the DCC val as being a local successor of the store, formally we would actually say that there exists a locally hardware required ordered before relationship between the write of the opcode and the subsequent DCC val, and more on that in the next lesson where we'll be exploring ARM's formal memory model definitions. Okay, next question. Do we need a barrier in between our data cache clean and our instruction cache invalidate? Well, again, let's ask ourselves, would it be bad if these two accesses were to be reordered with respect to one another? Yes, it would be bad. And the reason why may not be immediately obvious. You see, if the instruction cache invalidate were to be reordered before the data cache clean has actually cleaned out the new instruction opcode to the point of unification, then there's nothing stopping the I side from speculatively fetching the same cache line back in from main memory. This is one of the reasons why we always tell people the CPU is free to speculatively fetch from any region of normal memory at any time for any or no reason. And you must assume that it might happen at the absolute worst possible time. Like, for example, here, in this incredibly tight timing window in between us invalidating the stale opcode from our L1 instruction cache and us being able to hit on the new opcode that's being pushed out to the L2 unified cache. So, yes, it would be bad if these two accesses were to be reordered. And the next question is, can they be reordered with respect to one another? Now, you'd be forgiven for thinking, no. After all, these two cache maintenance operations are two overlapping addresses, and we just saw that creates a locally hardware required ordered before relationship between the store and the data cache clean, so shouldn't this also create a locally hardware required ordered before relationship between the data cache clean and the instruction cache invalidate? Well, now we've hit on the second of our three implications, that being that only explicit D-side accesses are hazard checked for local successors. The instruction cache invalidate is an I-side access, not a D-side access, so it's not hazard checked against the D-side data cache clean. So yes, these two accesses can be reordered with respect to one another. Okay, fair enough. So we'll need a barrier here. And wherever we need a barrier, we'll use a DMB, right? Well, now we've run straight into the third of our three implications, that being that a DMB only enforces ordering between explicit D-side accesses. The instruction cache invalidate is not an explicit D-side access, it's an explicit I-side access, meaning a DMB is not enough to guarantee sufficient ordering here. Indeed, let's take a closer look at what a DMB actually guarantees us. Now, I appreciate there's quite a lot going on in this table, but let's break it down a bit. So we have a bunch of different types of instruction, followed by a DMB, followed by a bunch of different types of instruction. So each column of symbols then tells you whether those types of instruction appearing before the barrier are ordered before the corresponding types of instruction after the barrier. For example, a DMB with any scope ensures that all data loads, data stores, and data cache maintenance operations appearing before the barrier in program order are observed before any data loads, data stores, or data cache maintenance operations appearing after the barrier in program order. However, you'll notice that even a DMB with any scope provides no ordering guarantees whatsoever with regards to instruction cache maintenance operations, TLB maintenance operations, regardless of whether they appear before or after the barrier in program order. So what does all of this mean for us? Well, it means we need to expand our toolkit with a new barrier instruction that provides stronger ordering guarantees than a DMB. And with that, allow me to introduce you to the Data Synchronization Barrier, the DSB. So a DSB is like a much stronger version of a DMB. The first thing you'll notice here is that everything after the DSB now has a green dot, meaning it is ordered by the barrier. And actually what's happening here is that the DSB is preventing architectural execution of any later instruction appearing after the barrier in program order. Not just explicit D-side accesses, but also instruction cache maintenance operations, TLB maintenance operations, and even other instructions that don't access memory at all, like an add. Now we'll come back to what I mean by prevents architectural execution momentarily, but there are two things I want to bring your attention to here. Firstly, the fact that a DSB does not complete until all qualifying memory accesses before the barrier have themselves completed. This is an important difference when compared to a DMB. So you'll recall that a DMB provides a guarantee that qualifying memory accesses before the barrier will be observed before any qualifying memory accesses after the barrier, when those accesses are eventually observed. But the DMB tells you nothing about when that will actually be. That is to say, when those accesses are actually observed is some indeterminate point in the future. Not so with a DSB. The DSB effectively stalls the CPU pipeline until all qualifying memory accesses before the barrier have completed. In other words, by the time the DSB completes and allows architectural execution of later instructions to proceed, we know for a fact that the preceding qualifying memory accesses have themselves completed. The other thing I want to raise your attention to is the fact that it is specifically an any scope DSB that will wait for all instruction cache maintenance, data cache maintenance, and TLB maintenance operations appearing before the barrier in program order to have completed. And, importantly, if that cache maintenance or TLB operation is being broadcast to other observers in the same inner shareable or outer shareable domain, then the DSB will also wait for responses from all observers in whatever shareability domain that is to have completed handling that operation. So for example, an inner shareable any scope DMB-ish will wait for responses from all observers in the same inner shareable domain. Speaking of shareability domains, you may recall this table that we first saw back in Lesson 6, which was summarizing the various DMB qualifiers. So there are 3 levels of shareability that we're already familiar with, these being inner shareable, outer shareable, and full system. But I mentioned back in Lesson 6 that there are also non-shareable variants that use the NSH or NUSH prefix. Now, we'll see how these non-shareable variants can be used with a DMB in the next lesson, but when it comes to using these non-shareable variants with a DSB, it's good to be aware that a non-shareable any scope DSB NUSH only waits for instruction cache maintenance and TLB maintenance operations to have completed on this CPU, rather than waiting for all of the CPUs in the same inner or outer shareable domain to have responded to all of our previous cache maintenance broadcasts. Okay, coming back to our instruction memory example. The qualifier we're going to use here is a inner shareable any scope DSB-ish. And that means that the CPU cannot begin performing the instruction cache invalidate until the data cache clean has completed. And that means even if the I-side does immediately refetch the same cache line after performing the IC eval, that's fine because the data cache clean will have already cleaned out that new opcode to the L2 unified cache and will be guaranteed to pull in the correct, most up-to-date opcode. Okay, looking good so far, but we're not done yet. Do we need a barrier here, in between the IC eval and the branch to the new opcode? Well, again, let's ask ourselves whether it would be bad if these two instructions were to be reordered with respect to one another. Yes, it would be bad, because if we were to branch to the address of the opcode before we finish the instruction cache invalidate, then we may still have a stale copy of the old opcode present in our L1 instruction cache, which we'll then hit on when performing our instruction fetch, which isn't good. Next question, can these two instructions be reordered with respect to one another? Or more accurately, can the instruction cache invalidate and the subsequent instruction fetch be reordered with respect to one another? Yes, they can, because again, only explicit D-side accesses are hazard checked for local successes. The IC eval is an explicit I-side access, not an explicit D-side access, and the subsequent instruction fetch of the new opcode is an implicit I-side access, not an explicit D-side access. So, despite the IC eval and the subsequent instruction fetch being to the same address, there are no ordering requirements here. Meaning we'll need another any scope DSB to ensure that the instruction cache invalidate is completed before we actually branch to the location of the new opcode. Okay, so we're done now, right? Well, no. Remember how I said that a DSB prevents architectural execution of later instructions? Strictly speaking, what we mean by this is that instructions after a DSB are forbidden from altering any state of the system or performing any part of their functionality other than being fetched from memory and decoded, reading internal CPU registers that do not cause side effects, and translating virtual addresses for memory accesses. And that first point in particular is a problem for us here, because it means the CPU can speculate past the DSB on line 6 and begin fetching and decoding the old instruction opcode from the L1 instruction cache before the instruction cache invalidate has actually completed. And that means we actually need another barrier here after our DSB, but before the branch to the new code. And that in turn means we need to expand our toolkit even further. So I want you to consider the following snippet of assembly code. Here we're writing to the Architectural Feature Access Control Register, CPACR, to enable floating point. And we're then executing an fmul instruction to perform a floating point multiply. In case you're not already familiar with them, D0 and D1 are 64-bit wide floating point registers. So this fmul is saying D0 equals D0 times D1. Now, with this code snippet as written here, there's actually no guarantee that the CPU will execute the fmul as expected. You see, the CPU may have speculated past the current program counter and already fetched and decoded the fmul at a time before floating point was enabled, meaning that when architectural execution eventually catches up to this point, we'll end up triggering an exception. In fact, even if the MSR had already been architecturally executed sometime earlier, it's still not guaranteed to actually have any effect on CPU behavior until the next so-called context synchronization event. That is to say, either taking or returning from an exception or executing an Instruction Synchronization Barrier, an ISB. So, an ISB effectively forces the CPU to abandon all in-flight instructions, flush its micro-op caches, and then synchronize processor context such that the effects of any outstanding MSRs are now in effect. So, in this example you see on screen, the CPU will first abandon the in-flight fmul, flush its micro-op caches, and then synchronize processor context so that the floating point is now definitely enabled. Finally, the CPU will refetch and redecode the fmul in that new context, and since floating point is now definitely enabled, then the fmul correctly decodes as an fmul rather than triggering a synchronous exception. So coming back to our changing instruction memory example, what we actually need to do here is combine a DSB with an ISB. Let's think about what this guarantees us. So firstly, the DSB does not complete until the preceding instruction cache invalidate has completed. It then follows that the ISB cannot be architecturally executed until the instruction cache invalidate has completed, because it appears in program order after the DSB. Now, it's possible that the CPU does speculate past the ISB here and fetches and decodes the old stale instruction opcode from the L1 instruction cache. And that's fine, because as long as the DSB itself remains incomplete, that old instruction opcode cannot be architecturally executed. Now, when the instruction cache invalidate eventually completes, that completes the DSB, and the ISB is then allowed to execute. That forces the CPU to abandon all flight instructions, flush its micro-op caches, synchronize processor context, and then refetch and redecode any instructions appearing after the ISB in program order. And that means if we did speculatively fetch and decode the stale instruction opcode, that's now guaranteed to have been flushed out, and we're going to be forced to perform a fresh instruction fetch, which is itself then guaranteed to pull in the new instruction opcode that was written by the D side. Now, a question I often get asked here is, why is an ISB alone not sufficient? Why do we need both the DSB and the ISB? Now, the problem with just using an ISB here is that when we reach the ISB, we'll abandon any in-flight instructions and immediately refetch and redecode them. But without the preceding DSB, who's to say that the IC-IVAL has actually completed? So we may end up just immediately refetching and redecoding the same stale opcode from the L1 instruction cache before the instruction cache invalidate has done its job. And again, the DSB itself also isn't enough, because the CPU can still speculate past the DSB and fetch and decode the old stale instruction opcode from before the instruction cache invalidate has done its job. It's only through a combination of both a DSB and an ISB together that we actually get the ordering guarantees that we're looking for here. And so this is our code sequence for modifying instruction memory. Now, you may have picked up on the fact that earlier I specifically said that the instruction caches are not guaranteed to participate in data cache coherency, and that we may need to perform manual cache maintenance in software. That's because some systems will in fact keep the data caches and the instruction caches coherent with one another, obviating the need for one or both of the two cache maintenance operations that we've been stepping through here. So this is reported by 2 bits in the cache type register, CTRL0. And these 2 bits are read-only, and they're set by hardware engineers at hardware design time. Now the first bit, IDC, instruction to data coherence, tells us whether the DCC vow is required. If this bit is set, it effectively means that the CPU's I side is able to snoop into the data caches, meaning there's no need to clean the dirty cache line out to the point of unification. Separately, the DIC field, data to instruction coherence, tells us whether the IC-IVAL is required. If this bit is set, it effectively means the CPU's instruction caches are participating in the hardware cache coherency protocol. In other words, cache lines held in dedicated instruction caches are tracked as being in either a shared or unique state, and any CPU issuing a transaction like a read unique or a make unique will cause those cache lines to be invalidated. Now, the way this usually works is that operating system kernels like Linux will sample these bits once during early boot and then runtime patch the affected functions and routines accordingly. So for example, here we can see the Linux kernel declaring an ARM64 has cache IDC capability, which will match if the has cache IDC helper function returns true. That has cache IDC helper function is the thing that actually samples the value of the IDC bit in the cache type register. And then here is an example of the kernel using this capability to runtime patch its dcache clean POU function, so as to skip the DCCVAL operation if the CPU supports IDC. And you may be wondering, is that safe? What if some CPUs support IDC or DIC while others don't? One could imagine a scenario in which we've patched out one or both of our cache maintenance operations, and then we later bring online a CPU that, for example, does not support IDC, and we then run into coherency issues when executing these patched routines on that CPU, since we're not performing the necessary cache maintenance operations that are required in order to guarantee correct behavior on that implementation. Well, thankfully, it's actually a requirement of the ARM architecture that all CPUs in the same inner shareable domain have common values for these bits. And that means it is safe for us to sample them once on the boot CPU during early boot, and then to perform this kind of runtime patching. And we're guaranteed that all secondary CPUs that we later bring online will share the same values, and so will behave correctly and as expected. Okay, that brings us to the end of lesson 20. Join me in the next lesson where we'll see how ARM formally defines its weakly ordered memory model in the ARM architecture reference manual, and we'll then learn how we can simulate that weakly ordered memory model and the effects of barriers using herd tools. I'll see you there. Thank you.